I'm really happy to be here. Also a professor of computer science, electrical engineering at Stanford University. I'm on leave at this company. The title is very misleading. It sounds very technical. I'm not here to give you a very technical talk. The subtitle is How to Get Rid of Road Congestion. Okay? That's what I've been working on for about 8 years. My area has been computer networks, which means internet algorithms, data centers and stuff. But I got into traffic because of being stuck in what I felt like really was a bad traffic jam in Bangalore. So this is in 2007, December. And it's one of those moments where you don't know whether, I mean, this just changed my life, but at that moment I just wanted to have a life after this incident, right? So my starting line for this talk usually is how many of you are stuck in traffic on your way here? Won't quite work. Actually, how many was anybody stuck in traffic? See, wrong. Okay, some. Wow. Okay. So, most cities already have this as a really bad problem. About 20 years ago, things weren't as bad just around the world as they are now, and it's only getting worse. Urbanization is the phenomenon of more people moving into cities and more people running into each other. And it's not just roads, this is buses in China. This is, I'm sure you guys have seen this video on YouTube, trains in Japan. This is the Shinjuku station. The people in uniform are actually employees of the railway company. So, and it's a proper job, it's called OSHIA, which means Passenger Arrangement Staff. Okay, so it has benefits, and this is not people just pulled off the street for afternoons or one rush hour. Okay, so it's a pretty chronic problem, and this is not something that's happening in small places, 3 to 5 miles. This is the mother of all traffic jams, 100 kilometers long from Beijing into Mongolia. And does anybody know how long this traffic jam lasted? 9 days, okay? So it's 100 kilometers, 9 days. It's the sort of stuff you can see from space, right? And so it's not, this is an engineering phenomenon, okay? It's not easy to put together a traffic jam like this anymore, right? This is now, you're in that 100-year traffic jams every day, okay? So obviously it becomes interesting to study them and then try to fix them or do something about it. And that's what I'm here to tell you about. One facet of it is to use data and understand why jams form, trying to elevate understanding traffic to the same level of let's say, rigor and intensity as people have done with weather. And after 40 years of studying weather, people have actually quite strong models for predicting and analyzing, understanding weather patterns. Okay, we're not anywhere near that for traffic. But the thing is, coming back to the theme of the talk, is not just commuter frustration and indignity. It's not just that. These things are pretty expensive. So Texas Transportation Institute releases a number called the cost of congestion in a report every year. And in 2007, we crossed 100 billion. It's in fact 2006, I think we crossed $100 billion annual cost of congestion. And this is the time and fuel wasted by vehicles stuck in traffic or moving slower than 60 miles per hour, let's say, free flow speed. That cost, if you're moving at 60 miles per hour, like at midnight or something, that is the cost of transportation. That's not included here. Okay, it's the extra time you spend. And, while nobody expects to take all of the $100 billion out, we can clearly expect to take down at least 10 or 20% of it, which is pretty significant. I mean, just consider the cost of auto bailout that we had to do in 2007, okay? And that's $25 billion, right? And this doesn't count emissions. It doesn't count safety. And I don't mean just road accidents, which is a bad thing, and it gets worse when traffic is high. It's also in public transport systems. People enter trains like in places like Beijing, Shanghai, Delhi, very crowded stations, but they're also open to the platform. So you can only come this way, and this is the platform, it's open. You cannot leave any other way than through the train. So if you don't have some way of knowing how many people there are and stopping people from coming, you're going to have a huge problem, right? So trains in London, in the London Underground, wait in the tunnel before they go to the station so that people who got off the previous train get time to leave. So people are doing incredibly detailed sort of things with traffic these days, okay? And I'm actually learning a fairly large amount of transportation engineering, okay, for a computer science type person. The visible problem is that demand is vastly bigger than supply, okay? That's obviously true. That's why we have this problem. And the economist's response here is to raise price, so impose congestion charges, right? So we have been doing some work on what if we pay people to take off-peak trips, right? So don't merely charge or don't just charge peak time commuters, pay the off-peak commuters some money. And I won't talk in detail about that, but that takes you into sort of large-scale behavioral economics experiments, which have been a lot of fun. If you're interested, I can tell you more, or you can look at my Stanford website for more details. What I want to talk about is transportation architecture, okay? So the real problem is data transportation architecture. Let me explain what that means, okay? In the 20th century, transportation architecture, or you can go all the way back to the Romans with this, by the way, okay? The first major road systems. There are people who either built or operated networks, whether it's train, bus, or road, or even taxi companies, right? There are those who build and run these things, and then there's us who use them, okay? And there's no direct relationship. We are sort of the side that imposes demand, and that side is who's giving the supply, but there's no direct link, okay? Now, who has done that, okay, in transportation? Well, back in the 80s and 90s, airlines did frequent flyer programs. For the first time, people just didn't enter a plane and know it's like TWA or Pan Am, but actually had frequent flyer accounts, right? So now you have a relationship with your passengers. And now, in the 21st century, of course, Uber, Lyft, and all these guys are doing it. Your relationship is Uber. It's not with the car. You're not sort of hailing things, right? So this is sort of the broken architecture. In the 21st century, we can use things like cloud, big data, and IoT, definitely 21st century technologies, to get real-time usage data and pass it on to commuters so they can make their own informed decisions on where and when they want to be and how much time they want to be spending. User behavior data, this means choices, preferences, what do people prefer to do, okay? And real-time analytics, okay, to the operators. This is all doable now, and I'm going to show you a demo of it. And I'm going to have to go over there and do the demo. And it's a live demo, means the data is not in my laptop, it's coming from the cloud, okay? So it's the honorable way to do a demo, but the dangerous way to do a demo as well, okay? So if it doesn't work, the organizers are going to refund your money back. Okay? So what does this look like? What's this architecture? The key enablers of this architecture are cheap and ubiquitous sensors. This is definitely a 21st century thing, okay? And abundant bandwidth. You could sense things, but we couldn't communicate it cheaply, right? Now it's like there's all these data plans that are machine to machine. That's almost nothing, okay? Plus, of course, the biggest sensor and communicator and everything is here, right? Every one of us pretty much has this, smartphones. And IoT, cloud, and big data are pretty much getting to the point of being ubiquitous and also almost commoditized, okay? So that's what's in favor, technologically in favor of things working. So if we look at all the things that move in a city, because you need something to start processing, there's GPS, there's smart travel cards, there's smartphones, there are even barcodes, like food is something that moves, and you can track the progress of food through a city. And this is not an idle sort of pursuit, like pretty serious food security. Many cities are now aware that they need to secure their food sort of delivery and supply chains, okay? Because if you have an outbreak, how quickly can you isolate contaminated food? And so the hope is, it looks good that there's a lot of data, but the problem with this data is that it's piecemeal, okay? So you can tap in and tap out with your smart card onto trains and buses, but you know how many people entered or exited stations, but actually don't know the train loads, which is what people want to know. So like in Washington, D.C., the metro, the people who go and have clickers and enter, 6 people enter the train, 1 per carriage, and within the next station, they start clicking around to count how many people there are. That's an example of something that systems do. There are also other systems which have surveyors standing on the platform looking at you, coming down an escalator, and you wait over there on the platform because it's very crowded, and it takes you a while to advance in the queue and enter the train, so you may miss 2 or 3 trains in the bargain. Okay? So that's the thing that they're recording. What quality of service are you getting? Okay? And train loads, there are trains that are now being built where the floor is a big weighing scale. Okay? So we can weigh all the people in it. We used to do this with cattle. It's now weigh people, divide by some per capita weight, and get a rough count. Okay? So this is sort of the clever engineering that people are doing. These trains are being sold. Okay? And the problem is that, the smart card company has that data, somebody else has this data, and you've got all this, it's not in the right place, and you can't put them together very easily. And also real-world data, analog data is very noisy. GPS is notoriously noisy, so it needs healing and curing at great speed at high volume. Okay? And silos exist. The operators of bus systems in cities are not the same as those who run trains, just different expertise. Contracts are given to different groups of people. They're intrinsically different. Okay? And so what's needed is a system and some algorithms for solving a massive jigsaw puzzle. Okay, that's what I'm going to show you, such a system and what it does and what it has done. Okay? Are you okay with this? So now you're going to see something for trains, taxis, buses. With that, I'm going to walk over there and give you a demo of a big data platform. This is a map of a subway system. All we know is where someone got in. This is how we assess fares and where they got out. We don't know what route they took, how long they waited, where they interchanged, but all that's inferable, and I will show you a demonstration of that. Okay? With that, I'm going to walk over there and hope everything works. This is a large metro. We have some real ones, but I'm allowed to demo something which we call Fredonia. So on the top, you see that there are 1.69 million passengers who rode the system on 15th of January 2014, sorry. Okay, and then they made a total of 3 million trips. Now this is the size of a system like slightly bigger than Singapore, close to Delhi, about 60% of the size of Hong Kong, just to give you some idea. Okay? And we just have tap in, tap out data, so we know where people have got in and out. So as I play this, against this ticking clock, what we're saying is this is literally what happened in your system on that day. So each of these moving rectangles is a train, and the amount of gray in this train is the number of passengers, so this is not as crowded as this train. So if I click on that, I can get the exact loads. So you don't have to send people with clickers, right? The data lets you figure out for every train how many people are in that train, okay? And these green bars are queues of people waiting at the platform, and some of these queues have got too long. So let's go to this Orion station and look at it in this direction. So you can see how many people have missed trains. So between 8 and 8:15, 276 people have missed trains, 0 trains, 327 missed 1 train, and so on. So exactly the sort of things you want to measure are all available just from this tap-in, tap-out data. Okay? And so this is sort of what big data can do. Lets you figure out all the performance measures you need to know to run your system. So now I'm going to move over to a demo of the New York City taxis. This is publicly available data that was released by New York City for the whole year of 2013. So this is a Sunday. Let me go to a Monday. Monday, February 11th, 2013. There are about 13,600 licensed taxis in New York City. And I'm going to play this. So all the blue circles are taxis that are hired, and the yellow guys are empty. Okay, they're looking for rides. So as I zoom in, you can see in the bottom left corner here, there are 4,200 taxis and 4,800 passengers in the viewport. So as I start zooming in, I can go and pick a particular taxi. So let's say I pick a taxi. Let's look at this guy. So I find out, how much this current trip is going to, give us a fare, and what's the total distance he's going to travel, the sort of things that taxi operators want to know. It's their performance measures, and then you can sort of follow the taxi. Okay, any taxi you choose. So when it's yellow, it's looking for rides. When it's blue, it's found a passenger. Okay. And now, with all this data, you get clutter. You can't see anything, so you can filter out stuff that you don't want to see. Let's say I want to look at taxis where the fare is at least $13. Okay, that's what it has. Let's go to $10. Okay, all these taxis are currently running, and the fares are going to be at least $10. Okay, so you can filter out a lot of stuff. What I really like about this platform is it allows you to query incredibly vast amounts of data, which is actually what a lot of the operators of these systems, whether train or bus or taxis, want to know. So let me start and say I want to look at this region. Okay, and I want to look at all the trips that start here. That's Midtown. And I'm looking at a date range. Let's say I want to do 20th of December to 1st of January, and maybe add a time range. Let's say 9 to 5, the working day. New York City people think they work 7 to 10, so let's just do 9 to 8 p.m., okay? 9 a.m. to 8 p.m., and then I want to plot this, and I want to look at the number of rides. There are a whole bunch of things you can look at, okay? On a per-day basis, and I want to break it down by date, and maybe I want to split it by fare. So what that means is I look for taxis where the fare is down here. So things less than $15, sorry, $1.5 and $10. Let's look at that. So now I plot this, and immediately I get the answers, right? So you can actually, this is what I mean by a big data system. You can choose your date range, time range, locations, and I have got a bunch of things I want to show you pre-prepared. You can save these reports. Let's look at some fun things about New York that we can learn from taxis. Okay? So New York City, like any other place, is congested. And the way it plays out for New York is the speed drops by 40%. So if you compare 7 a.m. to 9 a.m., the speeds are here, no matter where the trips start. Okay, they're all very low speeds, and between 5 and 6:30, you have huge speeds. And we know, in the interest of time, I'll conclude my talk, but we know how people tip when there's the Wall Street bonus week. Tips go up by about 9%, and if you can see what happens, the Knicks win games, how much people tip. And if they lose, we also know how much people tip. So this is what we can do with this data, and we know what the cool places to go to on Valentine's Day, in case you're interested. We're going to try and release this results in a sequence of releases. So stand by. But that concludes my talk. So what I hope you've taken from the talk is this: traffic is a phenomenon that mostly frustrates. But also, it is, at this stage, I would call it a scientific phenomenon. It's occurring every day, and it deserves to be studied. And after that, we can hope to mitigate it. Okay? And the difference between road congestion and nasal congestion, which is the other well-known hard problem for mankind, is there's no season for road congestion anymore. It's just throughout the year, and you're going to get it for 2 hours a day. If that doesn't happen in your neighborhood yet, don't move, it's going to come to you. Okay, it will be there. And our job is to try and stop that from happening. Okay, So with that, I hope you will come and check out some of these releases at Urban Engines later on as we do this sequentially. Thanks very much. Time for a couple of questions. I know how fast. So here's a question.
Hello, I'm back behind the camera here, if you can see me. Thanks, first of all, for working on what we refer to as a very unsexy problem. I'm curious what you think are sort of the next challenges for your startup, maybe from a usage perspective with urban engines, and how you plan on tackling those challenges.
So at the moment, we have data from a whole bunch of cities, whether trains or buses. We're probably the only platform that has been looking at this, the movement of vehicles and how crowded things look, okay, at the level of detail that we're doing it. And so this at least gets cities to understand, both on the operations and planning side, what they want to do. So that's a challenge Urban Engines is very much addressing, has taken up, let's say. The other thing is also there's an app. You can go to the either the Apple or Android stores and download an app called Urban Engines. So in a city that you are in, there are 20 cities where we have taken the data from the real-time GTFS data from buses and trains, and you can use the app as a transit app. So we want to find a way to give the information back to the commuters. And that's a two-sided approach. Work with the cities to help them understand congestion, help users understand and avoid congestion. So these are the major challenges that we are working on in cities that are also around the world for us that we are working on this problem.
Hey, I have a question. So I'm wondering if any of the data that you displayed is gathered live, and if not, how do you get it off of the train or wherever it comes from?
So in some cases, the data is available live, like this locations of buses and trains is available live. The taps, you have to tap out of the system, so it's not exactly live in that sense. I know, even if I know tap information at 5-minute or 3-minute sort of chunks, unless you tap out, I can't sort of reconstruct what happened. Right? Cities are also getting to the point where they want to make that data available to themselves in real time. Because they're now aware that sensing and big data together can really get them a detailed understanding of how the networks are not performing well. So here are a couple of things to just say along those lines. If you look at most cities, all the lines coming into the inbound, in the downtown business district area in the morning are crowded. All the outbound vehicles are usually pretty empty. So you're only using 50% of your capacity. And several cities want to flip these outbound vehicles back, bring them into the downtown area without sending them all the way back out, because you lose about 40-45 minutes of vehicle availability. And trains cost about $20 million, buses cost about $500,000. So these kind of decisions, if they're very well informed with exactly precise, do you do 1 in 4 trains of flipping around, 1 in 5 trains? That's the sort of detail into which this platform can get you.
Thank you.
And also real-time is very available for, I forgot to mention, a lot of the stuff that we're doing, we started with cities, but non-city transport operators like large-scale taxi systems, connected cars, logistics folks, packages also move. So anything that moves, as I said, food, those folks have also started, liking the platform and using it, which is a very different, there you can hope to get more real-time stuff, because most things are now, scans are taken from, handheld devices and so on.
Are you close to being involved in city planning? It sounds like the city I live in, I want you to design the transportation system. It sounds like it would save me some time. So, it sounds like you come in after the decisions have been made to try and fix it. Is there a plan in the future to take some of this data and say, here's the right way to design a transportation system?
Yeah, no, we are working with urban planners. So in Singapore, we have a contract with the urban planning department. And that is about getting to understand, not just, it's not that when you design something, you do this. It's not that. Even, when you look at buses, routes are almost always, there may be 300 or 500 routes, and about 5 or 10% of them are going redundant. Because this is the path that was active when this building was new, or the main employer was over there. And when that's changed, these routes still are around, but the traffic is not there, right? So they're almost always looking to see how to rejig stuff. Every city is doing this pretty much all the time. In terms of new cities, there are, and of course cities also want to know, should I go from a single-decker bus to a double-decker bus? There's all sorts of small, very important decisions that they're doing almost all the time. And in terms of designing new cities, I think what is the case is that pretty much every new city is now thinking of a fundamental public transport infrastructure, because there's sort of the idea that sharing the long mile and maybe doing exclusive trips on your short mile. So you drive from your house to the public train station, take a quick ride, and then on the other side, find a way to get a shuttle or something like that. That's the other short mile. This is something cities are doing.
Thank you.
Thank you.
Hi.
Okay.
I have a question. My name is Kathy Anderson. Speaking of the future of transportation and fundamentally changing our transportation architecture, is this data going to feed into, or are you working with the folks who are researching, thinking about driverless cars?
So, yes, definitely relevant. I mean, if car ownership fundamentally changes, I mean, a car manufacturer told me that the biggest problem for them with self-driving cars is the sales guys won't know how to sell a car if they don't appeal to the driver in you, right? If all cars can drive themselves, how do I sell a car to you, right? And this is a real problem, but it's something that aware is going to happen. Self-driving cars are going to happen. How long, where, etc., are some things that will gradually, be decided in regions. Policy and law are also, trying to figure this out. But inside large private campuses, like companies, there are small sort of golf cart style shuttles, which are fairly, almost robotic, pretty self-driven. They don't really need, the path is pretty clear. You can even mark with special, sort of signatures that you can read with a camera underneath the vehicle. And so it's not really a complicated system to design. And once you get people familiar with that, then doing it slightly, in the wild, they may not get so scared. So there are already steps underway. And of course, those guys, self-driving cars, use the network capacity really well. I recommend you check out phantom traffic jams, where there's no congestion, there's nothing, no accident. At some densities of traffic, we get too close to the car in front of us, suddenly brake, just a few of us do it, and then the guys behind us brake, and then from now on, the traffic is going to move in this caterpillar-like fashion, and the average speed drops. This is something self-driving cars can avoid, just because they don't have to worry about human reaction times. Okay, thank you.